Good morning and welcome to this week's CoE-MaSS seminar. Our speaker today is Budde. He is University of Free State. Prior to that, he was a postdoc at Northwest University and he obtained his PhD from Budde University. And Christian is talking about operator theory approaches, partial differential equations.
Thank you very much, Bruce, for this kind of introduction. Can you see me? Hey, maybe lift the camera just a little bit up. I know. Sorry for the inconvenience.
No.
Not the first inconvenience in my life. Regarding my height. So yeah, thank you very much for the invitation to speak in this CoE-MaSS seminar. I'm really flattered. It's actually my first time here at this university, so I think that's a good occasion. And as Bruce said, this is a talk on an operator theoretical approach to PDEs or partial differential equations by operator semigroups. And this is not going to be like a really deep research talk. It's more like a broad talk to give you an impression like what you can do with operator semigroups. And if you have questions afterwards, just don't hesitate to ask them. So I just want to mention there's a lot of research support from the NRF and also from the Center of Excellence for several projects. And I also want to thank, of course, my family for the support and also my whole department for the support and also for being here. And yeah, let's start, I guess. So let's start easy lemon squeak. So let's start with okay, let's do this. Let's start with ODEs. Go back to your second year of university. I think it's not sharing.
It is shared.
Yeah, but not my second page. I already swapped my page. Sorry. Maybe.
Is your screen on the second page?
Yes, yeah.
Yeah, so on the second page, yeah.
That's weird.
No.
So let me see.
So maybe
It's not
stop
sharing
here.
It's not showing the side for us.
Thanks.
Yeah, I think that then reshare again.
Share again. I'll just
Sorry about it.
That's okay. Let's go.
yeah, here we go. Okay. Okay, second page now. Okay, go back to your second year ODE. And the first ODE that you might have seen is U dot T is AUT for some, say, real number A. And then you know your Peano theorem, you know your Picard-Leonard theorem, all that kind of stuff that shows you there is a solution of that, and actually the unique solution of that particular solution. And I think it's quite straightforward what that solution is, namely the exponential. So let's do this. Sorry. So you know it's U of t is e to the power at times the initial one. This solves that particular ODE. Okay. So if we can do this, okay, we can do this in one dimension. The question is, can I do this in more dimension? Does it appear naturally? Yes, it does. If you solve systems of linear ODEs, yeah, then you rewrite this also as U of t is equal to AUT. A is not a real number now, but a matrix, right? An n by n matrix if you have n different ODEs. And also this has a particular unique solution, and this is also given by the exponential. So the exponential, how do you define the exponential for matrix? Now, the most straightforward way is doing it via the power series. So e to the power ta is then defined as the sum from n is 0 to infinity of ta to the power n. This makes sense. You can take any power of the matrix divided by n factorial, and then you multiply this whole thing. This gives you a matrix back. You can show that this is indeed a matrix, and then you multiply this with the initial value. This also gives you the solution e to the power ta at 0. How do you obtain e to the power ta? I mean, if A is a diagonal matrix, it's really easy. If it's not diagonal, just convert it to Jordan normal form. Then you see that the blocks, if you take to the power n, has a nice form, and then you translate back. Okay, so this is everything is finite dimension. So what would the next step be? Doing it in infinite dimension. Okay, so let's do an initial value problem in infinite dimension. And let's start with the easy case that I have a bounded operator. So what is the general setup? I have a Banach space, so I have a vector space with the norm. So the norm gives me the length of the vector, whatever that vector might be. Just think about R3, then the norm gives you the length of the arrow in the space. But it could be everything. Like you could speak about functions for that. And then you say, okay, A is now a bounded linear operator. So this means on the unit ball, you have some kind of boundaries. It's really nice. You can take you can take powers, everything makes. Just think about an infinite dimensional thing. Okay. And then you can also write down u dot t, so the time derivative, but then with respect to the underlying norm of that Banach space, because you're speaking about limit, right, is equal to a ut and some initial condition. Also, this has to be, you can prove that by the same techniques as you do it in the matrix case. And also here, u of t is e to the power ta exit. Okay, that's good. How do you define e to the power ta? If a is a bounded linear operator, also by the exit, right? So you write down that power series. This also converges perfectly because you have the triangular inequality. So everything works out very well. Okay. And what do you see here? What you actually obtain is that e to the power ta for every t gives you a bounded linear operator. And I put all these bounded linear operators together in a family. And I give it a name, namely TT. This will be something what we call operator semigroups at the end. And then we observe two important things. For example, if you take t is 0, what do you get? Then you get e to the power 0 times the operators of e to the power 0. This is just the identity. Okay? And you can also prove that t of t plus s is t of t times t of s. You just use your real analysis knowledge and do it for matrices or for linear operators. And the second property, and this is much more important, is that tt minus the identity goes to 0. So tt converges to the identity operator in the operator norm if t goes to 0. Okay, that's really nice. So let's give this particular thing a name. And we call it a uniformly continuous operator set. So let X be a Banach space, so norm, and the family of bounded linear operators on X is called uniformly continuous or uniformly continuous operator semigroup if these two properties that we just observed, because we already have an example, they hold. So T of 0 is identity, T of t plus s, T of s. So it actually commutes, right, the family, and that TT converges in operator norm to the identity. And then we say, okay, good. We already have a particular example, namely e to the power ta for some matrix. Follow-up question is, are there more examples? The truth is, no. Yeah. And this makes the uniformly continuous operator semigroups in some sense a little bit boring, not so very much useful, because the theorem tells us that if I have a uniformly continuous operator semigroup on a Banach space, then there exists already an operator. You can come up with a bounded linear operator such that TT is equal to e to the power ta. So all the uniformly continuous operator semigroups are already of the form into the power 2. There is no more. Okay. So far, so good. Other following up question. Are there operator semigroups, like families of bounded linear operators that satisfy the first property here, that do not have that second form? So is there a possible way to generalize? Unfortunately, yes, otherwise the talk would be finished by now. Yeah, so let's do this. Consider the Budde space of C0 R function. This is all the functions that vanish at infinity. And then we consider the so-called translation semigroup. So what do? You take a function, and tt of f of x is f of x plus t. So what does it do? It just shifts to that, right? It's a left translation. Okay. And what we observe, we can come up with some step function which is still continuous, and because it has compact support, it also vanishes at infinity. That all the functions for all t, they have supreme norm. Of course, I must say that C0R is a Budde space equipped with the supreme norm. So you take the maximum of the function, of the absolute value. And this, all the function ft, they have norm 1. But you can prove that tt minus 1, this is bound below by 1 for all t. So never converge. So this gives me an operator semigroup which is not uniform. And it does not say what I'm just talking about, that those translation semigroups are never uniform. I mean, there's that work by Johnson from 1978 on the uniform continuity of certain translation semigroups, the proceeding of the American Mathematical Society. There are some subspaces where this is possible, but in this particular case of that particular space, it isn't. So what you do, what we observe, it does not converge in the operator section. But because C0 function, and what do you see? F of x plus t minus f of x. This goes to 0 in the supremum if t goes to 0. And this gives me a new definition. This is what we observe, like tt f minus f in the supremum norm. This goes to 0 because I have a uniform continuity. And because you can actually show that this is true because CC of R, so all the functions with complex support, they are dense in C0 of R. Then you do the argument on CC on R, and then you lift it up with the depth. And this gives actually this particular continuity property gives us the new definition. So let X be a Budde space, and we call the family again of bounded linear operators, a strongly continuous semigroup or a C0 semigroup for short. If again I have the semigroup property, okay, that's always what we have to ask for. And the second one, that ttx minus x goes to 0 if t goes to 0 for all x and x. Okay, we saw already an example then with the translation semigroup. Another example is if I take a locally compact space R, just think about omega. Just think about omega as R. This is the most straightforward example I guess. And I have a function q which is continuous, and here you need some condition on the real part of q of omega in order to get indeed bounded linear operators. Otherwise, I don't get bounded linear operators. And then I do this. And what is this? This is just a multiplication system. We call it the multiplication. And you can also prove that this is C0 semigroup on C0 of omega. And even more, this is uniformly continuous. So again, recall that TT minus the identity in operator norm goes to 0, if and only if Q is bounded. Just mention that this condition does not give you boundedness, right? This only gives you boundedness of the real part, not boundedness in general. And so this semigroup is uniformly continuous if and only if Q is bounded. Okay. So we have the theory, and you can prove some nice things about that. And the question is, why should we study C0 semigroup besides that it's like a nice concept? I mean, not for nothing, there are books and books and books on operator semigroup. So what I want to talk to you today is actually the application to PDE theory. So just think about all your nice evolution equations. PDE, something like transport equation, wave equation, Schrödinger. I will actually talk with you about the transport equation in a moment. Then there are applications to probability, like Markov transition kernels, Brownian motions. There is applications in computer science. So think about time continuous automator model for time, a linear time invariant system. I mean, I put some of the books and reference here. So about the PDE stuff, there are the three main books. If I forgot the reference, please don't be angry with me because the space is just limited. There are more than enough references, but the main ones that I normally cite is that book from England, Nagel, operator semigroup. Then you have the book from Jürgen Goldstein and from Hardinger. So there are much more. There's also from Betty and Huber and Neubrander. But as I said, the space here. This is not comprehensive. Okay, so let's do some applications to PDE theory. Okay, so remember this was our definition. And what you might think is if I such a thing, and if I just going back to uniformly continuous n. Uniformly continuous n groups are of the form e to the power ta. Right? So what we have here is supposed to be the generalization for some operators of the form e to the power ta. Okay, if I just think about the function e to the power ta in the scalar, how do I obtain a back in the easiest way? What I can do, I take the derivative, then I get a e to the power ta, and then I evaluate in zero. So I take the derivative in zero. So let's do this. Let's make this a definition. So let tt be a zero semigroup on a Banach space, and then the infinitesimal generator, or just generator, is defined by, and what is this? This is just the first derivative in zero. And now we put all those x's together with this max x. I mean, we can do this. If this is useful or not, I mean, it is, but this is another question. So, in general, this is an unbounded operator because it's only partially defined in some subset, EA of S. Yeah. Okay. But what you can show, for example, A is a closed operator. What you can show is that DA, if you have a zero set group, this is dense. So this is already good. Yeah. And in particular, you have that this A is a bounded operator, bounded linear operator. So this means that the domain is everything. So I can make sense of that derivative everywhere, if and only if T is already a uniformly continuous semigroup. So this is another characterization of uniformly continuous semigroup. Okay. Still the question, what does this have to do with PDEs? Nothing so far, right? So let's discuss some examples. So we have the translation semigroup. So this is a C0 semigroup. So let's calculate the generator. Now then you see what is the definition. This is now pointwise, of course. Limit of t to 0 of tt f of x minus f of x. Now this gives me just f of x plus t. Now what happens if the limit goes to 0? Then I get the derivative. This is just the derivative in x. But what is the problem? If I take a general function from C0, those functions are not necessarily differentiable. So, and this is why you have to take care of the domain. because not all the functions are differentiable, but now you take all the functions where this limit exists together, and this gives them the space of all continuously differentiable functions that vanish at zero. And indeed, T of A is not equal to T0 of R, but I think a nice exercise that the A is indeed dense. So this is what I already thought. And I also promised that proposition, so that this T is a zero semigroup, that T of A is X, if and only if T is uniformly continuous. So in fact, this is not uniformly continuous, as we already have seen previously. And moreover, this is also quite important that TT, if this is a zero semigroup, then as I said, it's density defined, it's closed. And what's even more important that A determines the operator semigroup uniquely. Yeah. This is something what you admire, right? If you think about solutions of PDEs, then you want to have a unique solution. Okay. So we saw that for every C0 semigroup, I get a linear operator, an unbounded linear operator A, namely its general. So the question is, give me your favorite unbounded linear operator. Can I tell you, in theory, if this is a generator of a C0 set? This is the more difficult question, right? And the question is, yes, you can characterize those operators, and this is characterized by the so-called Hillier-Shida theory. So it reads as follows: so A is a linear bounded operator, linear operator in bounded space. Here AE, the following are equivalents. A is a generator of a C0 semigroup, satisfying that exponential value. So TT is bounded from above in all by M E omega T for some M and omega in R for all T. The question that you might have is that a restriction? No, because the uniform boundedness principle actually gives you automatically always such a bound. So there is always such an M, and there always exists such an omega such that I have this equilibrium. So we don't have to care about it. And this is equivalent, and this is now the characterization, of course, of those operators being generated of zero semigroup. A is closed, and density defined. This is what we saw already in the example. We didn't prove that, but like we saw this from the theory, from the example. And if for every complex number, if the real part is bigger than that omega, this omega here is linked to that omega. Then one has that lambda is already in the resolvent of A. What is the resolvent again? If you just think about matrices, it's the complement of the eigenvalue, right? So then lambda minus A to the power -1 makes sense. It's a bounded linear operator. This operator theory then. And then because it's a bounded operator, you can take all the natural power. And we will just abbreviate lambda minus A by R lambda, a resolvent operator. And this is then bounded above for all n by m divided by the real part lambda minus omega 2 power, which is the positive number we know. So the implication from A to B is the easy one, right? Because you prove, okay, I have this zero semigroup, then I can do all the estimates. And what's really important in this case is that if you have real part lambda bigger omega, then lambda is in the resolvent. And in this case, the resolvent can be represented by the Laplace transform. And if you have this, then those estimates are a little bit more convenient to know. That direction is the more complicated one. So the idea is actually that you use finite dimensional approximations or bounded linear operators to approximate your zero sum to construct picture one that we call. But I'm committed to it. So this is the Hillier-Shida theory. And in general, this is a really nice theory, but it's not really practical. Why is it not practical? because we need all the natural powers. So if you have to resolve it in some sense, then you need all the natural powers to prove something. So then there's easier way. So for example, if T is a contraction semigroup, so if N is 1 and omega is 0, then this simplifies to the so-called Luma-Phillips theory, and then the statement is much more then much more. Okay, so that's the Hillier-Schiller theory. Still, we haven't seen so much about partial differential equations, right? Except that if I have the translation semigroup, that we get the first derivative thing. But this is actually something which is nice. And I will show you why. Because what do you expect from a PDE? If you see a PDE, if you know the exact solution or not, mostly you don't know. So then most of the time you don't know. But what you want is that you can say, like in the case of the ODEs, I have a solution and that solution is unique. And that it maybe also depends continuously on the initial data. And this is what we call well-posted. Yeah? So a Banach space initial value problem, so this is abbreviated by ACP, this is the abstract Cauchy problem. And then Q from R plus to X is called the classical solution. If Q is continuously differentiable in X, UT is the T of A or T, and it solves the ACP, the abstract equation. I'm just keeping it simple. You can also talk about mild solutions. Let's don't do this. Just stick with the most straightforward definition of that. And we call the problem here well posed if for every x in D of A, there exists a unique solution, such that D of A is dense, and for every sequence, and here you see continuous dependence on the initial data count. Right? But xn converges to 0, then utxn also converges to 0 uniformly on compact open. And now we finally can link PDEs to operator semigroup, because for those operators, the associated abstract Cauchy problem here is well posed if and only if the operator A generates a C0 semigroup. So what does this mean for our context? If I have a PDE, if I can write this in some abstract Cauchy problem on an infinite dimensional vector space, and I can show that this operator I'm talking about is the generator of the zero semigroup, then the ACP is well posed, but this is equivalent because you equivalently rewrote this as from the PDE, then also the PDE is well posed. Okay. And here's the example. So consider the following partial differential equation, probably the most easiest to get thing. So the time derivative is equal to the space derivative with some initial condition, and here the G is in C0, so the space of continuously differentiable function that finishes. The question is, can I write this as an abstract Cauchy problem? Yes, you can. What you're doing, you take that PDE and you transfer it to that particular condition. So U prime of T is A of T, and without reading what's written here, okay, it's the classic. Now what must A be? On the left-hand side, I have the time derivative, this is why I'm using the dot. And on the right-hand side, I'm taking the space derivative. So the A of F must be F prime. And D of A is then, because we are in C0, we take C0, 1 of R. But that's good. Because what did we see about that particular operator? This is the generator of the particular C0 semigroup, namely the translation semigroup. So in particular, this is well posed, hence this is well posed. This has a unique solution that depends continuously on the initial data. And you can actually give the solution of FTX, then the FTX is TT applied to the initial condition, which is G of T plus. So you can recover your solution from the operator thing. I mean, if you have a this is a toy example, right? This is a straightforward, easy example, of course. But just think about the situation where your operator is super complicated. Then most probably you will not get the explicit form. But you know, there is a solution, and this is what you want, right? There is a solution and it's unique because the generator determines the operator setting group unique. Okay. Is that the end of the story? No, thank you. Because we can go on. As I said, this is a CoE example. So let's make this now, as I said, really complicated. I mean, there's so much application, so you can apply to population equations. So there's the work from Randy or that European group. This they work very hard on that. The positive operator topic group, there's a lot. There's that monograph by Arendt, the more recent one by Andrade, Budde, Marietta, and also after Randy. And I may not forget, of course, the positive people like Anke Karloff. She also works on positivity. You have Jochen Glück, Jonathan Mui, Sahiba Aurora. They all work on that kind of stuff. But I said limited, yeah. And I just want to put the main monographs, maybe the main reference. So please don't judge me. Then there's that work on control theory, which is really in and popular now. It's supported in the building system. Especially, I must mention the work or the group around David Jakob from Wuppertal. They received a really huge fund from Germany, from the DOT. It's called Sonderforschung, right? So it's some kind of like a excellent cluster. And they got now funding for working on post-quantum building systems. So, and they have a lot of PhD positions open currently. So I just want to acknowledge it. Okay. So here is your difficult operator. Yeah. Beyond C0 solution. Why beyond C0 solution? So take now the space CP of Rn, so this is all the continuous bounded functions. And then you take this following differential operator. And there's a lot of research about that. So there's that monograph from Lorenzo and Bertoldi, and also the more recent one from Lorenzi and Randy on that particular operator. It's actually, yeah, like linked to different statistical differential. So what you can show for each S in CP, there exists a solution. But even more, you can represent UTX, that solution that exists, by an operator center. However, it's not strongly continuous by any means. Yeah, like there is a subspace where it's uniformly continuous, but that's quite small. Yeah. So this is not strongly continuous, but nonetheless, you can say something about it. Yeah. And this gives you then the theory of. Okay, I still have, I think, 5 minutes. Okay. And this gives rise to the theory of non-strongly continuous angle. And this is something I actually worked on during my PhD, and I'm still working on it. So what is the setting now? I have the Banach space, and I equip it now with an additional topology, namely a locally convex topology. Not randomly, yeah, but subjected to some assumption. Maybe the norm topology is finer than the locally convex topology. Okay, that's X is sequentially complete of norm-bounded set. So what does it mean? If I have a two Cauchy sequence, the Cauchy sequence with respect to before, which is norm-bounded, then it's tau convergent. This is what I mean. And then X tau prime, so the dual space is norming. So I can actually express the norm of an element by taking the supreme over norm-bounded tau function. Examples, CB with the convex open topology is one. The point-wise topology unfortunately does not work, but the convex open topology works. Question why is if I equip CV of R with the compact open topology and I take the dual, why is it norming? Because in the dual you have all the point methods. So you can just make sense of that. Right. Continue. Yeah, continue. Then you can equip the L of P with strong operator topology. X prime, so the Banach dual with the weak star topology. And those spaces, I mean, this was in this idea of bicontinuity was originally introduced by Franziska Kühnemann. She was a PhD student from Rainer Nagel, which is my PhD grandfather in Tübingen. But there's a little bit more general setting about that it's called set spaces. And this is a book from J.D. Cooper on set spaces and application structure analysis. Also, if you want to read up on mixed topologies and so on, this is a really good reference. Okay, so this is the setting. And now I can define what is a bicontinuous semigroup. So a semigroup of bounded operators on a Banach space X, equipped with the additional locally convex topology 4 is a bicontinuous semigroup if it's okay. Semigroup is already equal, so you have T of 0 is identity and T of 2 is identity. So now TT is strongly tall continuous, not with respect to the norm, but now with respect to the weaker locally convex topology. There's exponentially bounded, and TT is locally bicontinuous. So, and here you see the interplay between norm and locally convex topology. So that every norm-bounded sequence which tau converges to 0, then TT also tau converges to 0 uniformly unbounded. First observation we make, every C0 semigroup is a bicontinuous semigroup. Then by taking tau is equal to the norm. Now that's the most straightforward. Other example, if you take, for example, the translation semigroup, we saw it's strongly continuous on C0 of R, but it's no longer strongly continuous on CB of R. Why is that? Because you can take, for example, the function f of x is sine of x squared. This is a bounded continuous function, but it's not uniformly continuous. And then you don't have TTF minus f converge to 0 in supremum. And I'm not saying bicontinuous semigroup is the approach to non-strongly continuous semigroup. I mean, there's a lot. I mean, there's the work from Priola on pi semigroup. There's the work from Markus Kunze on semigroup from norming dual pairs. And you have theory of operator semigroup on locally convex space, such as I hope I pronounced correctly, Komatsu and Ochi. I think there's a line over the OV6. Okay, but you know, there's a lot of other references. Okay, so what can you actually do with it? Examples, translation semigroup as mentioned. Then the dual semigroup on a dual Banach space. So if I have a C0 semigroup, what I can do, I can of course consider the dual operators of TT, so T prime of T, on X prime. But this in general does not give you a C0 semigroup with respect to the dual norm, but the bicontinuous semigroup with respect to the weak star. Then implemented semigroups. So there's this is actually work from Alder, who wrote an article on implemented semigroups. So why are they interesting? Why are they interesting? Because this is a natural thing that occurs in quantum mechanics. So it's implemented semigroup implementation that by operators that happens in quantum mechanics, but in mathematics quite rapidly. So this operator semigroup type TT C0 semigroup and ST is C0 semigroup, then script QT is also not a C0 semigroup, but a bicontinuous semigroup with respect to the strong operator topology. And it's the C0 semigroup, so this is the semigroup if and only if most of the operator semigroups here are uniformly continuous. So there you see why I also mentioned uniformly continuous. Then semigroups on the flows. So this is that work by Doro and Neuberger, and Ornstein-Uhlenbeck semigroup. I mean, there's the Faden, Navi, and Francis Bergman and Jan van Herm, they also across this, and there's like the whole Italian community working on Ornstein-Uhlenbeck semigroup on infinite dimensional CD. So we can do it on Rn, of course, that's already quite technical. Lifting it to a Hilbert space is a challenge. You can say something. Okay. So, and there's much more to say. I mean, you can use perturbation theory. So what is perturbation theory? If I have the differential operator, so if I have a PDE, then I split it in some part they know, and some part that I add to it. And then I want to still something say about solutions. So the perturbation theory actually for bicontinuous will start with the work of Van Farkas, who's I think supervisor. Then we wrote some articles together of the Schampacher perturbation for bicontinuous semigroup. Then as I already mentioned, the approximations. So you have that article by Kühlmann and Bakker, which is the title here. Then you can also do contour theory with Carsten Fude and Christian Weifert. Latter one's also a collaborator of mine. And then bicontinuous cosine families. So what are cosine families? Cosine families are kind of C0 semigroups, but they solve not the first order ACP, but the second order. So on the left hand side, you don't have U, dot U, but double U, double dot U. Yeah. And then you can also do something on flows or networks. This is a joint work with Marietta Kamas from Ljubljana. And there's more and more and more. You can do mean ergodic theory. You can, yeah. But yeah. And as I said, it's not comprehensive, just giving us a little bit of an overview. And I hope you got the message why C0 semigroups are important, and that there can arise really nice also masters and honors and PhD projects from that. And thank you again for listening and also for the invitation. Thank you very much.
Thank you. Are there questions from the audience?
Yeah. Yeah. Oh. Be speculative. Yeah. Yeah. You be involved. That's a good question. I mean, coming up with the result in general is a difficult task, right? Because I mean, if you want to solve this sort of lambda minus a x y, then you bring it to the other side, then you solve x as y, lambda minus a y, and then there's some ODE involved. I mean, even for the translation session, you only get an integral expression. You don't get like a really close expression without it. But I don't know if this really answers the question. I mean, you can use vector theory. What you see, for example, from the Hillier theorem, if I have a generator, then a half plane is the result. So the resultant is at least a half plane. And if you can say a little bit more, for example, if you ask for analytic, yeah, so then you actually see that the spectrum is in a sector. Then you like, because in a general theorem, I mean, we cannot say so much, except that it's not in a right half plane. But if you have analytic semigroup, I didn't mention that here, but then you actually see that it's only in a sector. So this encloses describes your spectrum a little bit in more detail. Yeah. And this is what I said, like you have the half plane, and this makes it a little bit easier to avoid singularity. Because then you can just take any company. It satisfies the cosine law, so it behaves like the cosine, So I think it's like C of t plus s plus C of t minus s is 2CTCS. So it behaves like a cosine. It's strongly continuous, or like in the case of bicontinuity, like co-continuous. And you can also attach a generator to it. So for example, if you take the cosine family, CT applied to a function is equal to a half of f of x plus t minus f of x minus t. This gives you a cosine family, as you might figure out. Yeah, but that's the thing about operators and also about cosine family. Because you have those generation theory, you don't need to say something about the solution. You actually don't maybe know what the solution is. So the thing is more about there exists a solution, and even with that you can say something about long time behavior, even if you don't know what the actual solution is. Yeah, there's that work from Budde and cosine families with Wenzel boundary function. So this is a little bit more involved in maybe the examples are a little bit more appealing than the one without boundary function. So there is definitely work on that. Okay, yes.
Are there any further questions?